And let me share screen. Okay. All right. So, yeah. So we left off last time talking about parameterizations. I sort of briefly talked about lines in space, but I do want to go back a little bit to some of this stuff. Let's see. We talked about like parameterizing the unit circle and how that's basically trigonometry. I think we did number 4, 5, and 6 here. But I wanted to talk about some of these problems before we go back to focusing on lines and lines in space. So yeah, if you're on the Zoom, remember just this handout's on the handouts page. So I would download it and open it. So I'm going to refer to it. Okay, so all right, let me go to the board then. So I do think there's something worth noting that I don't think I really did last time about sort of labeling a parameterization. Like once you draw a picture of it. So, all right, so more parameterized curves. So if we start with this example that we had last time of like, you know, x equals t, y equals t, parameterizes this sort of simple example. This parameterizes the line y equals x in the 2D plane, right? If you draw this, you can sort of think, well, I can actually label, it's a thick line. I can actually label points by the parameter at that point, right? I think I mentioned this before. It's like an address. It's almost like a way to address every point. It's like on a street where different houses have addresses, right? It's like the same thing, right? If we actually say this is 1, 2, 3, -1, -3, then I could also label points along here, right? This would be t is -1, t is -2, and then t is -3. So you can think about how the parameterization actually traces out the curve by sort of labeling. Right, I guess I did that maybe for the circle where I said like the standard parameterization of the unit circle where I said t equals 0 is over here, t equals pi/2 is at the top, t equals pi was on the left, right? 2 pi back over here and so on. So you can label that. And then I guess the thing, hopefully people on the Zoom can hear me. I'm assuming they can. Nobody said they can't. And if you just chat if you have a question. But if you try a different parameterization, you can sort of parameterize the same curve in different ways. So we could also do, in this example, I have like 2t plus 1, 2t plus 1, right? If you try that, maybe let's see, this one I put it in this pink color. Maybe if I do this in blue, right? Or maybe I should use a different, you can also change the letter of the parameter. Maybe I should call this like s or something instead of t. So now where is s equals 0? Yeah, it's at the same place as t equals 1, right? Where's s equals 1? Up here. S equals -1. When you plug in -1, you get -2 plus 1. So s equals -1 is down here. And then s equals -2. So first off, you see there that you could sort of just parameterize it. It's a different, it's the same, it traces out the same geometric figure, but you're tracing out, if you think of this as like a time variable, right? It's like a movie tracing this out, right? Then this is tracing out differently. This is actually moving faster. in some ways, going from -2 to -1, -1 to 0, 0 to 1. It's like going farther. But it's still tracing out the same curve, right? So that's why I say like same curve, different parameterizations. The problem with this subject is the word parameterization is so long. Whereas if I do something like in number 8, where you could use x squared, t squared, x and y both equal t squared, right? Or maybe I'll use a different letter again, x equals u squared, y equals u squared, right? Let me use green for this one. This picture is going to start to get kind of busy. Where's u equals 0? Yeah, it's the origin, right? Where's u equals 1? Same thing as here. Where's u equals 2? Yeah, I guess it's up here. U equals 2. What about u equals -1? Yeah, the same point, right? This is also u equals -1 and u equals -2. And so actually this kind of ends up tracing, I guess I could have put arrows on these, like if we trace an increasing t, the t comma t goes that way, the 2s plus 1 plus 2s plus 1 goes that way. The green one's a little weirder, right? It's like, maybe I should draw it again over here. It sort of traces, it's actually going really fast and it kind of slows down and then it goes back this way, right? So it's like goes in, if you're just increasing u. Does that make sense? And so notice it also doesn't trace the entire line, right? It only traces the sort of the first quadrant part of the line. Traces first quadrant. Okay. Right, so you guys, that's pretty straightforward, I guess. We talked a little bit about 9 and 10, I think last time, where what cosine and sine does, if you put 2t instead of t, it traces the circle twice as fast, because now it repeats at t equals pi instead of 2 pi. And we also talked about this one where you can actually just switch sine and cosine. If you want to start at the North Pole and go clockwise instead of counterclockwise, you could just do sine comma cosine instead of cosine comma sine. So again, I don't want to spend forever on this stuff, but just I will say, then also a lot of times we're going to restrict the parameter. So if you look at numbers like 11 through 14 and stuff, if we restrict the parameter, we can actually get pieces of curves, right? I mean, if you wanted just the first quadrant line, you could say this, but that's a little bit contrived. I might as well just say t comma t, but just have t only be greater than or equal to 0. If I just want the first quadrant piece, right? It's an easier way to restrict to a piece of a curve. So yeah, like what about let's see, pieces of curves. What about if I just said like x equals cosine, y equals sine, but pi over 2, t is between pi over 2 and pi, right? What part of the circle is that? The upper left, whichever number quadrant that is. I like that. Yeah, that would just trace out this from here to here, right? Because that's t equals pi over 2 and t equals pi right there. So if you wanted to just trace out a piece of a circle or something like that, you could do that. Yeah, we sort of talked about the next one, that we could cover it. If we just did 0 to pi, instead of 0 to 2 pi, we did cosine 2d to sine 2t. The line segment one is sort of interesting to me, right? So like, what if we want to parameterize a line segment? Let's think about this. So line segment from, this is definitely going to come up later. So from 3,7 to 5,-2. How would we go about trying to parameterize that? Yeah, Leah? That is good. That's actually the next problem says to do it that way. If we just wanted to sort of use our knowledge of lines that we had before vectors and stuff, how would we do this? Yeah, slope and point slope would give you this equation of the line, right? So what is, okay, so what's the line? What's the slope? Down 9 over 2. Over 2 down 9, is that minus 4.5 minus 9 halves? And so you'd have something like y minus 7 equals negative 9 halves x minus 3, which I picked some slightly unpleasant numbers here, but which is y equals negative 9 halves x plus 27 halves plus 14 halves plus 41 halves. Maybe something like that. And so you can then just use x as a parameter, right? So I could say x equals t. So then you could use x equals t and y is negative 9 halves t plus 41 halves. And what would the values of the parameter be? Yeah, between 3 and 5, right? Because it's x, since x is the parameter, and this goes from 3 to 5. So you could do that. That's okay. If you want to just parameterize, does that make sense that parameterizes the line segment? Basically find the equation of the line, use x as the parameter. But I think it's kind of nice to do, yeah, what it says in number 14, if you look at the handout, which is that basically there's a way to always do a line segment where t equals 0 is the starting point and t equals 1 is the ending point. And that's what we're going to care about when we move on to these line integrals, where we're going to actually integrate over curves or line segments and stuff. We're going to integrate some function over like a line segment in the plane. And then it's like we're going to need to be able to parameterize it. It's going to turn out. That's what we're going to need to do. So let me try this other way. Like Leo suggested. And then maybe I'll try to draw. Actually, so this picture of this line segment would be something like 3,7 maybe is up here, and 5,-2 is maybe down here, something like that. And so with the parameterization we have, this is t equals 3, t equals 4, somewhere in the middle here, and t equals 5. That's supposed to be the midpoint of the line, right? That's what we end up getting. But or one way to think about this is like, let's think about the vector. What's the vector from 3,7 to 5,-2? Two minus 9, is it? We go over 2 down 9. So that's 2I minus 9j. And so if we want, but we want t equals 0 to be the 0.3 comma 7, right? So we're trying to find this r. Remember, I could write these as in vector equation instead. I was writing them as x equals y equals, but I could say like r of t is ti plus negative 9/2 t plus 41/2 j, if I wanted to. That's an equally valid way to write down the same thing. It's just a vector form. So we want r of 0 to equal the 0.3 comma set, or 3i plus 7j, I guess, if this is vector notation. And we want r of 1 to be 5i minus 2j, right? If we want t equals 0, t equals 1. If we want to parameterize a line segment going from t equals 0 to t equals 1. And right, there's going to be something about scaling this by t. So if I draw this again, maybe I'm just going to erase these labels here and think about the new way that we want to look at this. So if this is t equals 0, and this is t equals 1. Can you see the blue chalk? Can the people on Zoom see the blue chalk? Blue chalk's kind of hard to see. Sorry, let me try green chalk. We want to make that t equals 0, and this t equals 1. If this is going to be sort of linear, where's t equals like a half going to be? Right in the middle, right? So t equals a half will probably be here. You know, t equals a quarter. T equals 3/4 should be there. And if we're thinking of this like vector wise, then this is like r of 0, right? This is r of a half. This is r of 1. We want to think of them as vectors, like I was saying about the arm of God tracing this, right? And so how do you do that? This is kind of what I was talking about at the end of class last time, is you start at the origin and you go out to the line, you go out to the t equals 0 point. So like to get to r of 1/2, right? I mean, to get to r of 1/2, follow r of 0 from the origin to the line. Then follow the v direction. V is this right here. Then go in the v direction, but how far in the v direction? How much of v? What's that? T, right, in general, but to go to 1/2, it's half of v, right? So if you want to get to this point, one way to do that would be to go from the origin out to here, and then to follow this, and then you end up there. Sorry, hopefully it's not too busy, the picture now, but right, you could get it that way. Then follow v for half the length of v. And if you think about it, that's really just saying r, in other words, r of 1/2 is 3i plus 7j plus a half of v, right? Actually, yeah, let me. This is also sometimes just called r naught to like represent just a point on the line that we're looking for. So really what I'm saying is go r naught plus half of v. because that's how we add vectors, right, is tip to tail. And so if we write that down, that's 3i plus 7j plus a half of 2i minus 9j. And this should give us actually the midpoint between the 2 points that we started with, right? So that's 3 plus a half of 2, that's 4i plus 7 minus 4.5 minus 9 halves. Math, 5 halves. 2.5. 2.5 halfway between 7 and -2. Might be right. Okay, so that's that point right there. So you can actually identify that point. And then similarly, just to check, R of 1 should be R naught plus 1v, right? Like if we go from the origin out to the line segment and then follow v the whole way for a whole length of v, then we get 3i plus 7j. Yeah, this better work because this is kind of how we found v, was subtracting the two. So when we add v back to the first point, we should get, yeah, 5i plus 7 minus 2 is, plus 7 minus 9 is minus 2j. And so that's just like a sanity check. Does that make sense? And that was my thing about, in general, this sort of suggests how you might want to parameterize a line in general, right? Because you go, certainly for a line segment, this gives you always the parameters t equals 0 to t equals 1, this kind of construction. And if in general, you could just keep going and like, I could keep going and have t equals 2 down here and t equals 3 down here, just follow the line farther, right? So in general, R of t is R naught plus TV. Make sure my pluses and my t's look different enough. Yeah, R naught plus TV. So if we want the line segment, that would be just t between 0 and 1. And if we want the whole line, that would be sort of all t. You could say t from negative infinity to infinity. Does that make sense? Right. And then I had those animations that were kind of illustrating that. It's not the exact same. I should have done the same one. Sorry, let me share screen. Yeah. Do I want to dare try to think I'm smart enough to actually change this to make it actually into that line? That seems like a dangerous proposition. It's not that bad. Okay, I don't know why I don't have this example to be like, oh my God, this is gonna be dangerous. We have an equation. What was the equation for that line? Negative 4.5x plus, what was it, 41 halves? Oh man. Let's go from 0 to 10. Okay, so now the arrow out to the line is supposed to go to 3, 7. This is so dangerous. So then I want the arrow, the orange arrow, to follow the line. Mathematica is not the easiest for making arrows and stuff. So, and then I want to use the parameterization that we just came up with. Actually, so the general which I didn't write down yet, the general parameterization would be, actually, let me write it down on the board. So if we just combine this, if we just really write, if we just finish the thought here from R naught plus TV, then you can sort of see it's like 3 plus 2t I plus 7 minus 9t j. And so this is x. X is 3 plus 2t. And y is 7 minus 9t. Okay. So I think I just changed these equations to that. 3 plus 2t, 7 minus 9t, and then, right, the red arrow is actually the same thing, but from the origin. Sorry, I don't know why I didn't think of that earlier. Okay, hey, look. So the origin's actually, whoa. So I'm only on the right half because most of the, yeah. So if I plug in t equals 0, for example, I get that point. Maybe I should do this from 0 to 20 to make it an actual square. Oh, wow, you can really see how steep the line is. What's negative 4.5 slope, right? So t equals 0 is that point. T equals 1 should be our thing there, which is 5. That does look, it's at x equals 5, y equals negative 2 is about right. Right, if we did 0.5, we end up at that point halfway between. You can actually play this like a movie. I think I can slow it down. Oh, it's going to come out of. So these are the various t values, right? If I try different t's, it actually traces the line. Does that make sense to everyone what's happening here? Just a lot of it goes off the screen, but we're actually tracing this line out. And if we want just a line segment, I guess I could make this go from 0 to 1 if I wanted just a line segment. And then we would see it's the dashed line is the whole thing, but that would actually be tracing out the exact line segment, right? Just from 0 to 1. Good? Good. Okay, maybe I'm belaboring this too much. All right. So yeah, so in fact, when we do this in general, you'll notice this is of these equations are of the form like these are linear functions of t, which sort of makes sense that linear functions to trace out lines. Linear functions of t. So you can imagine that in space, the same thing would happen, right? In fact, maybe I won't even bother too much to like, let me just actually share screen again and just talk this through. Yeah, so you can imagine in space, a similar thing would happen where you would have x, y, and z as just linear functions of the parameter t. And now kind of going backwards, we started with like 2 points, or we started with a line, a direction of a line, point on a line, and got these equations. Going backwards, if you start with equations like that, like at the top of the page here, and you actually try to interpret what they mean, right, I guess what I'm going to claim is that we have a line in space pointing in some direction, right? And if you sort of go backwards from what we just did, if you start with the linear equations and break it up into like the constant pieces, you put those together like that, and then you put the pieces with the t's in them together. So you break those up like that, which is kind of going backwards from the step that we just did here. Or maybe not, maybe it's that next step actually. And then you factor out the t. You factor the t out of here and you get that. Right, then you can actually see it's like the same thing. It's like you get R naught plus TV. If you plug in t equals 0, even all the way up here, if you plug in t equals 0, then x naught comma y naught comma z naught is clearly a point on the line. And since a, b, c, a comma b comma c is the direction, is the vector that you're following, then that is actually the direction of the line. So it's kind of nice. The coefficients of t, like in this example, give you the direction of the line. That was that 2, -9 that we had here, right? And then the constants give you the point on the line. So let me just write that down as like a general thing. So it's kind of nice. Like the generalization to 3 dimensions is actually just perfect. You just add a third coordinate. You don't really have to do anything else conceptually. Because you might think this is kind of silly for lines in the plane when we already understand lines in the plane so well. But when you go to lines in space, it's similar, right? R of t, I guess I said this at the end of class last time, but now we're back to this from a different direction. So R naught plus TV, where R naught is represents a point on the line, right? It's a vector, but it's from the origin to a point on the line. And V is the direction of the line. And if you write this out, I could write this out sort of, oh, my V's and my R's look kind of similar, don't they? Sorry, these are R's. That's an R. And I can almost go backwards through all this logic. And if I actually wrote down R naught was like X naught, Y naught, V naught, and V is A, B, C, you would get back to these equations, right? Like if this was X naught, Y naught, Z naught, and the line, the direction of the line was AI plus BJ plus CK. And then you sort of wrote all this out, you would get X naught plus AT I, Y naught plus BT J, Z naught plus CT K. And so this is your X equals that, Y equals that, and Z equals that. And again, if you wanted a line segment, you could do from like 0 to 1. And that would just go from the tail of ABC to the tip of ABC on the line. Or you can do the whole line. Makes sense. So, questions? Any questions or anything on that? I think that's maybe I've belabored it quite a lot. Go back to the screen share. Okay, so actually the last page of this handout is actually this idea that we can actually use, now that we know how to like write down lines in space, we can actually sort of solve some geometric problems, like give you some lines. So like at the bottom of page 3, this isn't too bad. You can write down what these 3 lines are. And then you can start to verify things like do these 2 lines intersect? Can I intersect this line with a plane? Can I find a point on a line closest to the origin? And these are all like solvable problems now. So what I kind of wanted you to do, I know we only have like 17 minutes left, but maybe you guys could get into groups. This is not too hard to write down. You really just do the same thing where you find the vector from the first point to the second point, and then use this as your R naught, and use the vector from this to this as your V, and then you can write down the equations. So you need to write these lines down because there's questions about them. If that makes sense. And we can start this and then continue it in class on Wednesday for a while. Sound like a plan? Sound like a party? Sound like The only thing you want to do in life right now. Okay. Can we get into groups? You guys know your groups. You guys can get into similar groups that you got into before, I guess. People online can write, can try, you can put stuff in the chat. I'll try to write the equations of the lines on the board at least at first. I mean, before the end of class. And then, but then it's really going to be about using these parameterizations to solve problems. So. Mute myself. So number 18 here, they're definitely parallel because the two vectors are parallel. So they point in the same direction. And then they're the same line. They might be the same line if a point, like, so the point -440 is on L2. That's one of the original points. And so if you actually set that equal to XYZ in the parameterization, if you get the same T, that means that that point actually does lie on that line. It turns out it does, right? That's what you guys just found out. It turns out L2 and L3 are the same line in disguise. So I'll talk about this on Wednesday just to make sure we're all clear. And then we'll try to solve some more of these problems. But it is kind of funny that L2 and L3 are the exact same line, even though they don't look like it. But I'll talk about that next time. Okay, so thank you. Please erase your board, straighten up your desks and all that stuff. And I will see you soon.